tough. So, yeah, can we start? All right. All right, so today we're going to talk about code inspection attacks and buffer overflows. Very exciting stuff. The slides have been mainly developed by Kamran, over there, Kamran Haider, who has also developed, has been, implementing the solution for the laboratory that we have taken from actually Nikolai Zeldovic's course, Computer System Security. And in general, it would be good to look at that website if you're interested in system security. All right, so first of all, why are we doing this lecture? This seems not to be hardware related. Well, I'd like you guys to really understand a little bit more about what this whole stack is all about. I mean, hardware is not, you cannot just understand hardware in its isolation. You need to understand how it works together with software. So today we're purely talking about vulnerabilities in software, focusing on buffer overflow attacks. We'll talk through these different versions over here. We talk about countermeasures, and then we'll go into more depth, where we will also have a separate slide deck that I will not give to you guys, but because it has the solutions or lots of solution material. But I'd like to show it to you so that you get some feeling for, what to do. So, first of all, we need to understand how computation really takes place. And what happens is that, and you may have seen it from one of the papers that you have been reading, is that, you have, a stack with stack frames, and these stack frames correspond to function calls, all right? So say we are right now in a piece of code, pointed at by f0, some kind of function, and we are calling an f1. Now, when we do that, we're sort of exiting the context of f0 and entering the context of function f1. So what are we doing? Well, we previously had a stack frame for f0 that contains all local variables, arguments, a return address and so on. I'll come to that in a moment. Now we're going to create a new stack frame, or start to do that, when we call f1. So what do we first need to know? We need to know where we can find the instruction once f1 has finished executing. So where do we find it? We find it right here. There's a return address f1 here that starts the stack frame for f1. Is actually going to point at the next instruction right after the call to f1. So we go back once we are done, and then we continue the execution of f0. Effectively, we would have popped off the stack frame f1 from the stack. We get to return address, we go there, we pop that off, and now we have all the local variables and arguments again available to us to continue computation in f0. So if we're building up the stack frame for f1, what do we add? Well, we have a saved frame pointer. The frame pointer actually points to a previous start of a stack frame. Why do we have that? Well, these stack frames are variable in length, and if we want to do debugging, we need to understand where to jump back to in order to, figure out what's going on. That's the main reason for having that frame pointer. Now, and then we have pointer to data. There's some data values maybe. There's local variables in general, but suppose in this example we have a buffer, and this buffer is going to be loaded with some data. So the whole idea is that we may have C library functions, such as these guys, that you could potentially exploit. So a malicious user can exploit this library to write beyond the size of an allocated array or buffer. So suppose I'm going to write inside the buffer itself some beautiful injected code, some shell code, which you guys will be doing in your laboratory. And in addition, we're going beyond the buffer's limits and overwrite all this other stuff, including the return address. So if we are going to pop off all this from the stack, we get to the return address, and suppose return address points at your injected code, then you start executing this injected code. Because you should not forget that you have a piece of memory where the stack is going from the higher addresses is built up to the lower addresses, but you know, the code is also stored in memory with and what you can do is when you pop this off the stack, it simply means that you shift the stack pointer up, right? That's all you do. You do not really delete anything that's written out here. So what it means is that you can actually, this return address then tells the processor to expect instructions at this location. But those are the malicious instructions that you now execute. So now you got an attack going on. So that's the general outline of the attack that we will talk about a lot. There are other kinds. Essentially, we have code. Usually, we have stack that grows downward and then we have a heap that goes upward. Heap is a dynamic memory allocation, and what the heap does is that it is not just a data. It's a data structure that includes functionality. So effectively, the heap, we will get to that, I think, at the later slides with an example. But the heap itself defines in C++ like, say, classes. And classes have virtual functions. And each member of a class can have its own implementation of such a function. And because of that, what you need to remember is, in your data structure, what you need to remember is the pointers, or what function implementation you would really want to have for that virtual function for your particular member in that class. So now all of a sudden in this heap you will see pointers appearing. And once you have pointers, like a return address, you can override them, and as a result you can potentially execute malicious code. So we'll look at that in a moment. Then we have dangling pointer references. So what happens here is that we have effectively a pointer to a memory location that has already been deallocated. But you know, dereferencing of such a pointer is generally unchecked in the C compiler. What does dereferencing mean? I look at the pointer and I simply look, so the pointer still exists, and I simply look at what value is stored at the address indicated by the pointer. That's dereferencing. And then I will, learn something, but you could also jump maybe to something else and so forth and create an exploit, for example, modification of a newly allocated object through a dangling pointer. This is what we call dangling pointer, of a buffer previously allocated at the same memory space, or manipulating and exploiting the Linux memory allocator through dangling pointers. So we'll not go into detail on that one, but you could do that too, and you have hopefully read about it in the paper. The format string vulnerabilities are very interesting also. Now, if you have a printf and scanf functions in C, right? Well, what does it expect? Actually, the specification just expects to see literally, a string, a whole bunch of characters and something of a certain format, a string format. Okay. Now what happens is that if you expect to see, let's do this particular guy, if you expect to see a percentage %d, you expect to actually retrieve from a stack corresponding to the printf functionality to a integer, right? A percentage %d is that you want to see an integer variable. Now, it may be the case that I have not added an argument here. Doesn't matter. The compiler does not raise an exception or what. The point is that you still pop off the stack a value. So if you do that repeatedly, you could potentially go towards the location of the return address and then figure out what that is. Or in this particular case, if we have a percentage n, which is a very special type of command, it says it stores the number of characters printed so far at a location pointed by the argument, at a location that is pointed by the argument C, right? So if you're a bit familiar with pointers, then this language explains to you that this actually retrieves something that is then being stored in there. So that's kind of interesting, because what I could do is I could have a pointer to the return address, and then actually create some gibberish, if it's something like this, that I put down there, and then the whole thing may crash, for example. Let's look at another format string vulnerability. There's a whole bunch. I put in an extra reading, if you're interested. It explains a bunch of things, and one of them is this one, that I found quite nice, so I added this in this presentation, in this lecture. So, say we have a main program, and what are we doing? We do a scanf, so we want to have some user input, like in the form of a string, and then we are going to do a printf of the user input, and that's a vulnerable place. Now, why is that? The user input I can construct in a special way. For example, like this. What is happening? Well, if I do that, first of all, I'm reading the user input, so I actually store it into memory. All right, so here it is. This simply means that I store a hexadecimal number 10 and then 014808. It's all down in here. Then I have this percentages x that essentially tell me, so what does that mean exactly again? Actually, I forgot. Yeah, percentage x. I think it means that you retrieve hexadecimal number, right? Okay, so good. So that's what you then, but this is like a value, right? Right now, because this is a string, but you store this in here. Now let's have a look. Suppose I'm going to look at this print command. So where it is? Here it is, print command. And suppose it's issued right here. So I have an address to the user input, right? That I want to now push through the printf input, if you will. So that's the input. So, okay, I'm going over here, and I'm going to first look at this. So I'm going to see this. So it's the user input, so I print it, or I show this, fine. Then I have this, and it says retrieve a hexadecimal number. So what does it do? It looks at the next point in the stack, because that's where it was, and it retrieves this. Then it looks at that, it retrieves that. It looks at that, retrieves this, looks at this, retrieves this. And now it looks at percentage s, which simply means that you print the value corresponding to this address. So that's pretty cool. So now you will print the value pointed at by this particular address, and that is the attack, right? So now you can find out, for example, certain values or whatever you want to use this attack for. So I thought this is pretty cool, because this sort of explains a little bit how an actual unchecked format, if you will, because the compiler doesn't do that, will then go through this whole sequence and then does something bad.
Won't the C compiler cause an error?
No, it does not.
Because it usually doesn't like when you put percent signs in your user-defined string. I'm trying to put that.
Yeah, no, it's no, because you are just, well, there will be more of an application wrapper around this scanf, right? So if you are reading user input and the user input looks this strange, you often would like, in your programming, a piece of code that checks whether the format that you require for the application, that is actually guaranteed. So you want to interpret the string in a certain way. But if you interpret it in this hypothetical way, to some extent, right? If you immediately print it, then you would immediately have a vulnerable place. But the compiler does not check it. No. So if you would want to create your own exception as an application designer, you need to certainly do that. You need to make sure that the format is being checked, essentially. That's important. Yeah. May give a warning, though. So we'll come to that later. So what about countermeasures? So there are safe languages, which is pretty cool. You can have like Java, safe dialects of C. So that's pretty nice. So what do they want to do? They want to essentially eliminate certain types of vulnerabilities, in particular the ones that we just discussed. We have bounds checkers. What does that mean? Well, every array indexation pointer arithmetic is checked to ensure that a read and write to a location outside the allocated space is not attempted. So you want to make sure that you do not go beyond the buffer limits, right? That's what you want. Probabilistic countermeasures, we will talk about those in a moment. Canaries, we will explain in a moment, but the idea is that you put in some secret random number at a certain spot so that if you overwrite it in order to get toward the return address, you overwrite that number and you will detect that something is wrong. That is essentially the whole idea behind this. Memory obfuscation, sure, you can do some encryption. It's usually expensive in performance, but therefore you do it with a simple XOR often. But anyway, you could do actual memory obfuscation by encryption, but usually not done. Memory layout randomization. Well, in order to make attacks work, you need to know where your shellcode is located, right? So you need to know where the buffer is located that you write it in. So you need to know something more about the memory layout. So if you can randomize it and you obfuscate that kind of knowledge to the attacker, then that would be a good countermeasure. All right, so other countermeasures, right? Virtual memory management. All right, what about virtual memory? It's an abstraction above the physical memory pages. We will explain more about all of this next lecture and maybe the lecture after that. But the point here is that the virtual memory pages can be assigned read, write, and execute permissions. And that's essentially what the application is looking at. So these permissions can be used to construct countermeasures, for example, non-executable memory-based countermeasures. So we talk about that in a moment as well. Hardened libraries, where we replace the library function with versions with extra checks. So maybe now, if you look at the compiler, then hopefully well, it depends a little bit. You would like to see a warning if you simply do a printf of an input, of some user input that essentially represents a string that is a variable, right? So you would like to have a warning out there. But that has nothing to do with hardening library functions though, but you can harden library functions as well. So make it more safe. Runtime taint trackers, meaning that if you get input, you would like to know where the input comes from, and when you are dealing with the input in your computation, you want to find out, you essentially assign trust to the output of your computation, depending on where that input came from. So you have these taint trackers that essentially will tell you, how much essentially you believe that the computation is done correctly. And we'll look at that also at the hardware level at some point, much later, I think after the spring break. We hopefully have some time to talk about that as well. For a hardware, in the hardware, as a hardware component, hardware module. All right, so how does a buffer overflow work? Now, I've explained it a little bit, and here it is. Actually, let me go through this. Otherwise, I'll have to walk back and forth. So we have something of this form. We have this stack frame of my function, a return address, which goes to the next instruction after you've called my function. So what's the problem? Modifying the return address somehow to point to an arbitrary location can be exploited to execute some arbitrary code, and that's a buffer overflow. So let me actually put all this out as well. So what we would like to do is to somehow override the return address to point at a piece of malicious code, right? That's what we want. So the key observation 1, the attacker can override the return address, make the program jump to something else, like what the attacker chooses. And the attacker can set the return address to the buffer itself, actually, which is kind of interesting, so that it points inside the buffer where it could have stored the malicious code. So that's what we're talking about. So, so how does it firstly know the address of the buffer in the memory? Well, often the virtual memory makes things more determined. So actually, there's not much randomness involved, really. So you can actually predict those addresses. For a given OS and program, the addresses will often be the same. As a matter of fact, in your laboratory, you will use a tool GDP, right, to have a look at, you will find out the addresses of where, the different, where the return addresses are stored and so forth. You will figure that out, where that is. So why would programmers write such code? So legacy code wasn't exposed to the internet. Programmers were not thinking about security, right? It's only something for the last years. And many standard functions used to be unsafe. So that's pretty bad news, obviously. So what's the payloads of a buffer overflow attack? So what can we do? Well, we can use any privileges of the process. In particular, if the process is running as a root or administrator, it can do whatever it wants on the system. For example, if you have your Linux installed and you want to install, say, a virus scanner, right? Well, in order to run the virus scanner, you need to be a root or administrator, and then you scan your Linux virtual machine, for example, to check on what, if there's something bad. But after that's done, you better log out as a root or administrator and log back in at a lower privilege level, because if there's malicious code, it would inherit essentially the privilege of of the code that is broken. So that could be as the root. So you want to do those kinds of things to be safe. So even if the process is not running as a root, you can do all kinds of things that is bad. And oops, what am I doing? So what about the OS? So why didn't the OS notice that the buffer has been overrun? Well, unfortunately, the OS, does not see anything strange. Given the spec and everything that's going on, there's nothing strange. It does not violate any rules, you see. So the OS only gets invoked when the application does an I.O. to some inter-process communication, for example. Other than that, the OS basically sits back and lets the program execute, relying on hardware page tables to prevent processes from tampering with each other's memory. So if we will talk about how that works next lecture. However, the page table, which essentially helps you to find out where things are stored, right? Those protections don't prevent buffer overflows launched by a process against itself, right? Because that's what's happening if you put in some kind of a string that the application asks for. It's just something, that process runs on its own. It's not coming from the outside, according to the process, it's coming from within itself. So, an overflow buffer and return address and all of that stuff are inside the process's valid address space, and that can be manipulated with the buffer overflow attack. So, of course, it can make buffer overflows more difficult by having some of those countermeasures, for example, address memory layout, randomization, stuff like that. Avoiding buffer overflows, well, of course you need to avoid bugs in C code. Well, that's kind of hard. But build tools to help programmers find bugs is a great thing to do. Formal verification methodologies, people do that. Actually, there are tools out there. But still, you do not know whether you're completely secure. And memory safe languages. So, avoid the bugs in the C code. So, clearly, you could carefully check the sizes of buffers and so forth. And modern versions warn you when a program uses unsafe functions, which is great. So what you definitely should not do is, ignore compiler warnings, because your program can still run like properly, but you want to make sure that you deal with those with respect to security issues. So deal with those warnings. It's good, avoid problems in the first place if you're very careful, of course, if you can really do that, but it's a pretty hard task. It's hard to ensure that code is bug-free, and we talked about that in our previous lecture, right? Because there's so many lines of code and you really don't know. You cannot just verify everything, particularly if the code base is large, right? So the application itself may define buffer manipulation functions which do not use these types of primitives. So you do not really know, the compiler doesn't really know and does not really see whether something could be dangerous. So no warning is even issued. So, we can use static analysis to find problems in source code before it is compiled. But by statically analyzing the control flow, for example, we can tell that an offset is used without being initialized. That would be pretty cool. The bad thing is it's difficult to prove the complete absence of bugs again, right? We don't know. Good thing is that even a partial analysis is useful. You make it harder for the adversary, which is great. So there we will talk about Becky bounds in a moment, Becky bounds checking. Well, this is just an example. It cannot catch all the memory errors, but it can detect many important kinds. Becky bounds checking really means that you, for each pointer, you really remember the base where it starts in your memory, and also how much memory is allocated to that in a smart way. So yeah, you'll have to be careful. Everything